Bismillahirrahmanirrahim. Today we will study the gravity dam, and because these are the most widely used dam nowadays, and we will study this and we will design this, and we will also design another dam. So criteria for selection of a dam site, construction material, forces acting on gravity dam, modes of failure, its stability analysis, safety criteria. So all these factors we have to keep in our mind, and we have to go through all these processes, all these terminologies. So gravity dam has been defined as a structure which is designed in such a way that its own weight resists the external forces. This type of structure is most durable and solid and requires very less maintenance. Such dams are constructed of masonry or concrete. However, concrete gravity dams are preferred these days and most widely constructed. So the line of upstream face or the line of the crown of the dam, if the upstream face is sloping, is taken as reference line. That is called baseline of the dam, axis of the dam when suitable conditions are available. So this is an example of gravity dam. We have 56 meter here, and we have a vertical. If this small triangle is not present, then this is called as vertical face. So this is called heel of the dam, this is called toe of the dam, and here we have 75 meter height. This is 9 meter, this is 4 meter freeboard, 6 meter crest, and this is the maximum water level. This is the upstream face, maybe vertical or slanting. So this is vertical face and this is the slanting face. So these are the forces acting on the gravity dam. We will study these forces one by one. Water pressure, uplift pressure, pressure due to earthquake, silt, wave, ice pressure. So first of all, water pressure, that is the most major external force acting on such a body or dam. The horizontal water pressure exerted by the weight of water stored on the upstream side can be estimated from rule of hydrostatic pressure distribution. So when the upstream face is vertical, the intensity is 0, and at the surface, water surface, and equal to gamma h at the base, where gamma w is the unit weight of water and h is the depth of water. It will act h by 3 from base. Like this is the dam body, this is vertical face, this black line, this is the vertical face, and these colorful lines, these red lines represent the water pressure. Water pressure will be 0 at this surface, and water pressure will be maximum at the bottom, at this baseline. So at this point the water pressure is maximum. As we are coming on upstream, on upper side, then water pressure is decreasing. So water pressure will act at h by 3. So this is h, head of water. Water will act at h by 3 from the bottom, and water pressure, total water pressure will act at this point. And this is not a slanting face, this is sloping face. This face is sloping. Here we have water, here we have water. This will be called as P1 and this will be called as P2. And we will study in the design. So water pressure is equal to 1 by 2 gamma w h square, and this will act at 1 h by 3 at this point in this straight face, vertical face. So when the upstream face is partly vertical and partly inclined, the resulting water force can be resolved into two components, vertical and horizontal component. And horizontal will be equal to this and act at h by 3 from base, and vertical component is equal to weight of water stored in that column A, B, C, A, like this one, A, B, C, again D and A. So water stored in this column, we have to add the weight. This is vertical component, this is horizontal component. So if water is also present on the downstream side, that is called H dash, that is called as tail water, then it will also act force on this body. And if this slope is always slanting at slope, this face is always at slope, so there will be horizontal and vertical component. Horizontal component will act in this P1 dash, and vertical component will be PV dash. Like at this place, horizontal component was P1 and it is PV. Vertical, so here vertical will be PV dash, horizontal will be P1 dash, and its H will be changed to this H. And this maximum force will be equal to gamma WH. Here maximum force will be equal to gamma WH dash, force of water on the dam body. So that force is stabilizing the dam, and that force is opposing the dam body, and that is basically damaging the dam body. Next is uplift pressure. The water which is being seeped from the upstream side, the seepage line, that may called a vertical uplift pressure in upward direction below the body of the dam. So this is the uplift pressure. The dam may face uplift pressure here with no drainage gallery. If there is drainage gallery, then uplift pressure will be divided into two components. One component will be from at this point, because we also study the maximum pressure at this point is gamma WH. So at the first line of uplift pressure will be equal to this one, gamma WH, and next it will be decreasing, and at this point, from this to heel to toe, at this point the gamma WH will be converted into gamma WH dash. So here the difference of drainage gallery, at drainage gallery gamma the uplift pressure will be equal to gamma WH dash plus 1/3 gamma WH minus gamma WH dash. So at this point this value will be at this point and this value will be at this point, but now we have to join them by straight lines. We have to join this. If we get a vertical line here, a vertical line here and a vertical line here, then we can join straight line here, straight line here and straight line here. So basically uplift pressure is little bit reduced where we have the drainage galleries. So water seeping through the pores on upstream side, cracks and fissures of the foundation material, and water seeping through dam body and then to the bottom through the joint between the body of the dam. It is the second major external force after the water pressure and must be accounted in all calculations, such as an uplift force vertically reduces the downward weight of the body. So because the main thing in this gravity dam is the weight of this body. The weight of this concrete body is basically acting downward, and this weight basically resisting all the external forces, the force of wind pressure, wave pressure, ice pressure and water pressure, uplift pressure. So when there will be uplift force in upward direction, it will reduce the net weight, the total weight of the dam, and it may cause severe threats to the dam body. The amount of uplift is a matter of research, and the present recommendations, the uplift pressure intensities at the heel and the toe should be taken equal to their respective hydrostatic pressures, which we calculated. When drainage galleries are provided to relieve the uplift, the recommended uplift at the face of the gallery is equal to this one, this one, gamma WH dash plus this one. So it is also assumed that uplift pressure are not affected by the earthquake forces. The uplift pressure can be controlled by constructing cut-off walls under the upstream face, by constructing drainage galleries, which we discussed, drainage channels between the dam bodies for its foundation, and by pressure grouting the foundations. If the area is under continuous earthquake, and then earthquake forces must be considered, and the earthquake, the allowance must be made for stresses generated due to earthquake. An earthquake produces waves which are capable of shaking the earth upon which the dam is resting in every possible direction. So the effect of an earthquake is therefore equivalent to imparting an acceleration to the foundation of the dam. It gives an acceleration in any direction in which the wave is traveling. Earthquake waves may move in any direction, and for design purpose it has to be resolved in vertical and horizontal component. So two accelerations, one horizontal alpha dash h and one vertical alpha v dash, are induced by earthquake. The value of these acceleration are generally expressed as percentage of acceleration due to gravity, 0.1 g or 0.2 g. These are considered. So on an average, alpha equal dash is equal to 0.1 to 0.15 g is generally sufficient to high dams in seismic zones. In areas of no earthquake or very less earthquake, these forces may be neglected. In extreme seismic regions, the value may be 0.3 g, sometimes be adopted. However, for areas not subjected to extreme earthquake, it may be ignored, or 0.05 g can be taken. So effect of vertical acceleration. A vertical acceleration may either downward or upward in case of earthquake. When it is acting in upward direction, then foundation of dam will be lifted little bit upward and become close to the body of the dam, and thus effective weight of dam will increase, and hence the stress developed will increase. It is a safer side. But the most dangerous side is when vertical acceleration is acting downward. When the earthquake, the vertical acceleration which is induced due to earthquake is acting in downward direction, then what will happen? The foundation on which the dam is resting, that foundation will move away from the dam body, and it is the worst for the design. Such relaxation will therefore exert an inertial force given by this, that is equal to mass into acceleration. So W is the total weight of the dam, W over G into alpha V dash, and G is acceleration due to gravity. So net weight of the dam will be equal to W, total weight of the dam, minus W over G into alpha V dash. So we have to keep this factor in our design. We have to increase the dam weight, and we have to keep our dam stable. If we want to keep our dam stable, then we have to consider this factor, which may reduce the net weight of the dam at earthquake when the acceleration will act in downward direction. So alpha dash is equal to kV into G, where kV is fraction of gravity adopted for vertical acceleration 0.1 or 0.2. G is acceleration due to gravity, so alpha can be calculated here. So then the net weight of dam will also be equal to alpha dash will be replaced with only kV into G, and you can see it is G will be cancelled, W into 1 minus kV. So in other words, vertical acceleration reduces the unit weight of dam material and that of water to 1 minus kV times their original unit weights, and kV is equal to 0.1 or 0.2. If kV is, for example, 0.1, then its answer will be 0.9. That is the worst for the design. So effect of horizontal acceleration may cause falling two forces, hydrodynamic pressure and horizontal inertial forces. So horizontal acceleration acting towards the reservoir, when dam body will act toward the reservoir, causes a momentary increase in water pressure, because if dam body is moving toward the water pressure will increase. As the dam body where water is resting, the area will little bit reduce due to movement of dam body towards the water body. As the foundation and dam accelerates toward the reservoir and the water resists the movement owing to its inertia, so pressure will increase. This external pressure owing to its inertia, the extra pressure exerted by the process is known as hydrostatic pressure. According to von Karman, the amount of hydrostatic pressure PE is given by this one. If dam body is moving toward the water from right to left, then this will be the PE, and its center will be at this point. It will act at this point, 0.424H, and its value will be 0.555 kH gamma WH square. So P is this, it will act at height of this from the base, and KH is the, where KH, this KH is fraction of gravity adopted for horizontal acceleration 0.1 and 0.2 as we studied for kV. So gamma W unit weight of water, so PE will be equal to 0.424. This force will act at base, PE into H. You can see this one. So moment will be equal to 0.424 H multiplied by PE. So moment of this force is this one. So we have to calculate all the moments. Then we have to use some moments which are supporting the dam body and some moments which are opposing the dam body, and we have to add some factor of safety in the design. So I will share a design video, then we will discuss. Next is silt pressure. It has been explained under reservoir sedimation that silt get deposited against the upstream face of the dam, and H is the height of the silt deposited. Then the force exerted by silt in addition to external water pressure can be represented by Rankine's formula, that is equal to 1/2 gamma submerged weight of soil particle H square into Ka, and Ka is equal to 1 minus sine theta over 1 plus sine theta, where theta is the angle of internal friction of soil, cohesion is neglected, and gamma submerged weight of water, weight of silt particle, H is height of silt which is deposited, and it will act H/3 from the base. If the upstream face is inclined, the vertical weight of silt supported on the slope can be act as a vertical force. In the absence of any reliable data for any going, so type of silt is going to be deposited. So the total horizontal force will be equal to this one, and vertical force will be equal to this one. So we can see total horizontal force, so this is wave pressure, so that is the silt pressure. And that is this, with respect to H, height of silt which is present there. In most of the gravity dam design, silt pressure is neglected. Why silt pressure is neglected? Because initial the silt load is not present. That may be time becomes significant when it is get deposited, and when it get consolidated to some extent, then it is not considered as fluid acting on right or left or vertical direction. It usually support the dam body then. So silt deposited in the reservoir is somewhat impervious and therefore help to minimize the uplift under the dam, and it support the dam. Next is wave pressure, wave generated due to winds on the surface of the reservoir, which causes a pressure towards the downstream side. Wave pressure depends upon the wave height, and height may be given as this one, and B into F. F is distance. If this equation is valid for F less than 32 km, V is the wind velocity in km per hour, and this equation is valid if the distance is more than 32 km. And wave height means the distance from top of crest of wave to the bottom of trough of the wave in meter. So F is the fetch or straight length of water in kilometers, so water expanse or wave. The maximum pressure intensity due to wave action may be given as PW is equal to 2.4 gamma W HW, and act as HW by 2 meter above the still water surface. HW is wave height. So this is wave. So this is wave. Its PW will act at the distance from the trough will be equal to, up to this one is equal to HW by 3, and wave is 2 by 3 on the surface, and wave is acting 1 by 3 below the surface. So this is the wave, this is the trough, this is the crest, and this is the HW. From this one to this one, that is HW. HW 2 by 3rd part of HW is on above the water surface, above this line, where 1 by 3 part of HW will be below the surface, and from surface 3 by 8 HW, this will act as PW, and PW is also acting here at HW by 8. So the pressure distribution may be assumed to be a rectangle, to be a triangle, 5 HW by 3. So the total force due to wave action PW is equal to this one, or PW is equal to 2 into gamma W. HW square is equal to this one, and this is equal to 19.62 HW. It is function of HW square, and this force acts as a distance of 3 by 8 HW above the reservoir surface. This one, from this one up to this one, that will be the wave pressure will act at this point, and it may not cause a serious threat to the dam. Next is ice pressure. The ice pressure which may be formed on the surface of the reservoir in cold countries, that may sometime melt and expand. The dam face has then to resist the thrust exerted by the expansion when water will converted, when top surface will be converted into ice. This force acts linearly along the length of the dam and the reservoir level. So the magnitude of this force varies from 250 to 1500 kilonewtons, so a usual value of 500 kilonewton per square meter may be allowed under ordinary conditions. So this ice pressure may be taken. Weight of the dam, the weight of the dam body and its foundation is the major resisting force. So the only resisting and supporting force, that is the weight of the dam. In a two-dimensional analysis, a gravity dam, a unit length of dam is considered with the weight of dam for 1 meter in longitudinal direction. So the combination of forces for design can be considered for two cases: when reservoir is full and when reservoir is empty. So you have to just calculate all the forces which are opposing the dam and all the forces which are resisting the dam. If for example water pressure is opposing the dam body, wave pressure is opposing the dam body. Similarly, you have to consider all the forces which are opposing to the dam body and weight of the dam and any other force which is supporting the dam body, and then you have to calculate the momentum for all the bodies, and then you have to subtract, see the difference of forces, difference of momentum, which we will see in the design of the dam. So when the reservoir is full, this is the case 1, the major forces acting are external water pressure, uplift pressure, earthquake forces in seismic zone, the silt pressure, ice pressure if temperature drops below 0, and if in cold countries. In Pakistan, I think ice pressure is not a problem, and wave pressure for the most conservative design, and from purely theoretical point of view, one can say that a situation may arise when all the forces may act together, but such a situation will never arise, hence all the forces are not taken generally. So normal load conditions. Normal load, there are two types of classification: normal load combination and extreme load combination. So first is the normal load combination: water pressure up to normal pool level, normal uplift, silt pressure and ice pressure. This class of loading is taken when ice force is serious. Water pressure up to normal pool level, normal uplift, earthquake forces and silt pressure. Third one is water pressure up to maximum reservoir level, maximum pool level, normal uplift, silt pressure without ice pressure. And what is the extreme load? Extreme load means water pressure due to maximum pool level, extreme uplift pressure without any reduction due to drainage gallery if there is no drainage gallery, and silt pressure is also there. Case 2, when reservoir is empty. Empty reservoir without earthquake forces to be computed for determining bending diagrams, and similarly empty reservoir with a horizontal earthquake force produced toward the upstream has to be checked for non-development of tension. The tension at the toe of the dam should not be there. Types of failures which can be there in the concrete gravity dam: by overturning or rotation above the toe, the dam may be rotated above the toe; by crushing of dam material by development of tension due to causing ultimate failure by crushing; by shear failure called sliding. If dam slides from upstream to downstream, the failure may occur at foundation plane, at the base of the dam, or any other plane at higher level. So first one is the overturning. If the resultant of all the forces acting on a dam at any of its section passes the toe, and dam shall rotate and overturn above the toe. Practically such a situation shall not arise, as the dam will fail much earlier by compression before overturning. So the ratio of the righting movement above the toe to the overturning movement above toe is called factor of safety, and this factor of safety is kept as 2 and 3. And we will see this momentum and these two types of momentum, the opposing and supporting momentum, and we will see the factor of safety there. Compression or crushing. A dam may fail by failure of its material. If material is crushed due to compressive stresses produced may exceed the allowable stresses of the material which is used in dam construction, and dam material may get crushed, and the vertical direct stress distribution at the base that is given by this equation. So that is equal to direct stress plus bending stress, and E is eccentricity of the resultant force, sigma B is total vertical force, B is the base width. So this is the case, and this is the total B divided into two components, and this is the resultant force, this is the vertical, this is the, if acting on any point in the dam body, this is sigma H, and this is heel, this is toe. If forces are acting on this point, then this is toe. The dam body may rotate in this direction above the toe. So at this point, this should be positive. The P min should be positive. So this one, the total stress P max and P min, the P min should be possible. It's positive. It should not be negative. It should not be in tension. If there will be tension, the material will be highly compressed, and the compression may go beyond the compressive stress of the concrete material used there, and the material may get crushed, and dam failure may occur. So the masonry or concrete material has its own tensile stress for high concrete gravity dam. So are usually designed in such a way that no tension is developed anywhere in the dam, because this material cannot withstand sustained tensile stresses. If subjected to the excessive sustained continuous tensile stresses, this material may finally get cracked. And however, for achieving economy in design of very high gravity dam, certain amount of tension may be permitted under severest loading conditions in order to save the economy, in order to keep the B bottom width of the dam body minimum. This may be permitted because of the fact that such worst loading conditions shall occur only momentarily for a little time. So the maximum permissible tensile stress for high concrete gravity dam under worst condition can be taken as 500 kN per square meter. Effects produced by tension cracks in a dam. When such a tension crack develops, say at heel or crack with loses contact with the bottom, so the crack width loses contact with the bottom foundation and thus become ineffective. So the effective width B of the dam base will be reduced. So let me show you. If this is a total B from this point to this point, it is the total B. If the material get cracked here, it will lose its contact with the foundation. So the effective B means the foundation width from this point to this point, the width of the dam body which is actually strongly in contact with the bottom foundation. So the effective B will be reduced. For example, if material gets cracked from 0 meter to 5 meter, so the 5 meter soil, the dam body will get ineffective and B will be reduced. So what will happen at the reduction of the B? So the effective width of B of the dam will be reduced. This will increase P max at the toe. Hence a tension crack by itself does not fail the structure, but it leads to failure of structure due to excessive compressive stresses, and these excessive compressive stresses basically crush the material which is used for construction of the dam. So in order to ensure no tension is developed, we have to keep that P min should not be negative. It should be at most equal to 0. So P min can be set as 0. When you set it as 0, then you find the equation E is equal to B over 6. So the maximum value of eccentricity E that can be permitted on either side of the center is equal to B by 6, which leads to famous statement: the resultant must lie within the middle third portion of the dam. So B by 6 means the resultant force will lie within the middle third portion of the dam. So you can see here old uplift diagram, new uplift diagram after cracks, AA dash has developed. So new uplift diagram AA dash, you can see here that the original old uplift is here. We have, so the dark line, the complete solid line, this line and this line, this line. So A, B, C was the original uplift diagram. So what will happen when cracks are developed? Crack from A to A dash, crack is developed, so new diagram will develop. That may cause damage of the dam. Sliding, the last one is the sliding. Dam may get slide when net horizontal force above any plane in the dam or its base exceed the frictional resistance developed at that level. Because the dam is stable due to frictional resistance developed in the material, if the force acting from left to right in this way may cause little bit sliding of the dam, that is also dangerous. So the friction developed between two surfaces is equal to this one. Sigma h is less than mu into sigma v, where mu into sigma v over sigma h represent nothing but factor of safety. It should be greater than 1. In some cases it is preferred it should be greater than 1.2. So this factor of safety will save the dam body against sliding effect. In low dam, the safety against sliding should be checked only for friction, but in high dam, For economical precise design, the shear strength of the joint is also considered. So equation for factor of safety against sliding, which is shear friction, become, so shear friction is equal to this one plus this one, where B is the width of the dam at the joints, Q is average shear stress of joint, which varies from 1400 to 4000 kN per square meter, and mu is generally from 0.65 to 0.75.